Okay, so we are going to look at a topic known as related rates, and this is an application of derivatives. We've learned all the various rules for finding a derivative, and we talked, if you remember, about applying it in the sense of that a derivative is a rate of change. And in this section we're going to look at relationships between rates of change, where two or more quantities change, for instance with respect to time, but their rates are related to one another. In order to get going, though, I want to do a little review, because in setting up the relationships that we'll be doing the calculus on, we need to remember some pre-calculus relationships, some geometry relationships involving things like the Pythagorean Theorem, right triangle trigonometry, and other such things. So let's just briefly review this. Here we have a triangle, as you see, and what I'm interested in is relating the values of x, y, and d. Well, if you notice, x and y and d are the various side lengths of a right triangle. You can notice this is a right triangle. And I hope what jumps out to you right away is the Pythagorean Theorem. So in other words, we can relate the values of x, y, and d this way. If I square the sides lengths and add them up, they will equal what? The square of the side opposite the right angle, the hypotenuse. So in this case we would have x squared plus y squared, the sum of the squares of the two side lengths, or two legs of the right triangle, equals the square of the hypotenuse. And there's the equation that we would have. In number 2, we're going to look at relating the area A of this right triangle, and we're going to relate it to the values of x and y. Well, of course, the area of a triangle is just 1/2 the base times the height. And we notice in a right triangle that the value of x, if we think of that as being the base length, then y is going to be the height, because that 90-degree angle is there. And so we simply have that the area, capital A, is 1/2 x times y. So I hope those two are very simple for you. Those are examples of the type of thing that we'll be doing. Let's look at a couple more, though. Suppose I wanted to relate, down here in number 3, theta to x and y. Well, now we're going to be looking at the trigonometric identities, the trigonometric ratios, rather, for a right triangle. So if you remember the phrase Suckatoa, or the way I remember it, some old horse came a-hopping through our alley. So sine is what? The opposite of the hypotenuse. Cosine is the adjacent over the hypotenuse side length, and tangent is the opposite over the adjacent. So we look at relating the angle theta to x and y. X in relation to theta is the adjacent side length, and y is the opposite. So which trigonometric function relates the opposite and adjacent side lengths together? And the answer should be tangent. Right? Tangent of theta is going to be the opposite over the adjacent, so y divided by x. So one way to write this relationship is simply that the tangent of theta is the opposite side length, which is y, over the adjacent. Now another way you could have done this also is with the cotangent function, because it's the reciprocal of the tangent function. So cotangent of theta is the adjacent side length over the opposite. So cotangent theta would be equal to x divided by y, which is another way it could be written. What about relating theta to y and d? So y is the opposite side length, and d is the hypotenuse. So which trig function are we going to use there? I hope you said sine. Sine is the opposite, y, over the hypotenuse, d. So I can write the relationship as follows. Sine of theta is the opposite side length, which we said was y, over the hypotenuse, d. Okay. So those are some easy examples. What we're going to do is I'm going to stop the video now, and then we're going to, the next video, we're going to take a look at the process of related rates and how this comes into play, and then of course where does the calculus come into play.